Hi, everyone, and welcome to DeepStation featuring Leandro Lima, machine learning engineer at Block, known for Square and Cash App, and formerly machine learning engineer at Meta with a PhD in computer science. We are super excited for today's session. And Leandro, how about you introduce the topic of this next session?
Cool, cool. Hey, Grant. It's nice to be back. So today we are basically continuing last session, but instead of just seeing concepts, we're gonna show some code. Um, so what I recommend in this session is for people to, know the basic of Python and know how to create a Jupyter notebook. Um, so we're not gonna teach exactly like how to set up these tools, but I think it's easy to download from anaconda .org, or even, in my case, I'm using VS Code, Visual Studio. You can also use Cursor. I believe there's a list of tools that you can use. Or even if you don't want to install anything, you can use Google Colab to run your code. So the link will be available. You'll be able to, people will be able to download everything that we're doing here today. But instead of just seeing concepts, we're gonna see some coding.
Amazing. And before we started, we were talking about how thankful we are of what you are doing here, Leandro, making machine learning accessible to people around the world. I think it's a very dense and to a lot of people intimidating topic. I actually saw that in a comment today. So, and they said that videos like what you're doing is very incredible to make it more accessible, and they're very excited to
Amazing,
watch. So
amazing, amazing, amazing. Yeah, this is something I love to do, and I'm looking forward for the next ones and this one.
amazing. Well, I'm going to go ahead and share the screen, and we can get started.
Awesome, awesome. Okay, so yeah, I promised to show some code, but we're gonna see a new topic with just some animation here. So last time we learned how linear regressions work, linear regression, and based on linear regression, we can create logistic regression. That's a classification algorithm. Um, so today we're gonna use logistic regression and KNN. KNN is K nearest neighbors. Um, and it's a very interesting algorithm because when you see it working, you will learn that quick.
Mhm.
Okay, so basically, suppose we have our data set, right? And let's say we have two classes. Let's call this class A and class B. So they're divided this way. I'm again using interactiveml.com. You can just go to the KNN uh, session, or just type, you know, knn.html. So how does that work? Um, so we have our data set here, right? These are points in the space. It doesn't have to be 2D space. What the algorithm does, it trains based on, well, it makes the predictions based on who is closer to the point, right? So let's say I want to make a prediction of a new point that's in this region. What do you think this would be, Grant? Red or blue?
I would guess red in this case.
Red, right? Because it's closer to the red dots, right?
Right.
So here, what the algorithm will do, and the test points are green here, is to check the k. In this case, we're setting k as 3. So it's going to be the 3 nearest points to the new point, and it will do a voting, you know. The class that has more of the nearest neighbors will win, right? For example, if I click, let's say I click here, then my all my 3 nearest neighbors are from class B, blue, right? What if I click here? So here it's an interesting case because I have one um, of the A class and 2 of the B class, right? But in that case, B is winning. So as you can see here, we'll have class B as the prediction because we have 2 of the B and 1 of the A. And you can always play. There is no right number here. Of course, there are ways to do, an analysis to find the best uh, number of neighbors that you can check, but you can always play and increase that to 5, I don't know, 7. So whenever you click, you will always see, oh, in this case we have 8. Let's decrease to 7. So class A got 6 points and class B got 1 point. So the chosen one will be class A, right? In real life, the points are not as beautiful as these, but it could be something similar, right? So what I'm going to show today is how to use both logistic regression and KNN to make predictions about the iris dataset. Okay. So let's start presenting our notebook. So I do have another notebook that's a little more robust and has more information, but I decided to create a simple one uh, just to show the basics, right? So here in the beginning, we're just importing a lot of libraries. So we are using mainly a library called scikit-learn or sklearn, and you're gonna use logistic regression in this model called neighbors classifier, which is KNN, and a few functions to get the metrics. Interestingly, there is also a function to load specific and more famous data sets, and there's an easy way to load the iris data set, right? So we're gonna just load the data here and split the 2 variables, the main matrix, which is X, and the target variable, which is basically the name of the flower. Let's go back here real quick. So just to...
We love our iris data set, and I love how easy they make importing it.
Yeah. This is the previous notebook that's more complex, but yeah, I'll share in another session. But again, just to review it, we're trying to classify different types of flowers based on the sepal and the petal length and the width, right? Okay.
Oh, and
So
I should mention for the audience real quick, we will go ahead and you could look in the description here and you will see the GitHub repository, notebooks, and all the information you need for this session.
Exactly, exactly. Yeah, so here we're just splitting our variables into what we call a data frame, right?
Mm-hmm.
Well, maybe some parts will be confusing and hard to understand in the beginning, but think of a data frame as a matrix, right? So in Python, we can define different types of variables, floating number, string, text, an object, and one of these things that comes from pandas is a data frame. So think as an Excel spreadsheet that's saved into a variable, and you can basically analyze rows and columns, passing um, some indices. Okay, so what we are constructing here is a data frame called df. It's getting the y variable and creating a target column, um, and it's renaming it to 0, 1, and 2 just to you know make the predictions um, more, it would be better for the algorithms to have numbers instead of text, because we're dealing with numbers, right? So when you run this cell here, um, all it will print is the data set shape, which is basically the number of rows and number of columns, and the classes, right? So if we do df.head, it will show a few rows, and then we can see, well, this is the x,
Mm-hmm.
this is the df. The df has 1, 2, 3, 4, 5, 6, right? Um, Let me see. Sample. This will choose 6 random rows from the data set, just so the audience can see. So Virginica was remapped to 2. Here, Setosa was remapped to 0. And well, actually, I think it's the opposite, because the target probably comes as a number. Let me see. Yeah, there you go. The target comes as a number, and then well, the remapping is basically just to show what the species is. All right. Okay.
Makes
So
sense.
here we're going to create some plots. This will be a correlation plot, um, pair plot. We're using this nice library called Seaborn to make the plots. What I want to see is how the different values here, sepal length, sepal width, petal length, and petal width, relate to each other. Um, so this is what this plot is doing, and boom,
Look at that.
this is amazing. So much information here. So let me explain what's happening. So each row of the plot is a different variable. Um, each column is a different variable as well. Um, So here we're trying to see if there is a correlation among the variables, and how the different species look like in the space. So yeah, last time we were trying to classify some species, and well, we can see that in some cases only one variable is enough. For example, petal length. If you just set a threshold here, it's able to separate setosa from versicolor and virginica, right? So versicolor and virginica seem to be closer to each other. Um, in that case, we'll remove the setosa to make our problem a little harder. But okay, so this huge plot here, the pair plot, is made of two different things. One is the correlation plot. It's basically just showing the actual number. Each point is a sample here, and it's showing x and y axis. So the x-axis will be what's in the bottom here. So here we're comparing sepal width to each of these other variables here. So sepal width versus petal width, sepal width versus petal length. In the case where we have the variable against themselves itself, um, instead of having the actual plot, because this will be just a straight line, right? We're
Right.
using histograms. So the histograms will just show the concentration of values um, in a specific region. For example, so here we can see that the sepal length of the setosa is between maybe 4 and 6, right? So it will always be in this region. See,
Yeah.
if we take the x-axis, and here this is showing the same. So there is more concentrated in the middle, a few here, a few here. The versicolor, it's more in the middle region. You can see here. So in the virginica, the green one, it's more towards the right, from the middle to the right. So that's what we see here. Here, there's one sample here that's represented here. This sample right here. Okay, so in this case, we can see, hey, if we take, yeah, looking at the histogram, we can see that petal width by itself is able to separate setosa from the other two, right? So if we set a threshold here, for example, or here for petal width, yeah, here for petal length and here for petal width, we're able to separate at least setosa from the other two classes. But if we look at sepal width only, it's pretty mixed up, right? Um, in that case, we would have to combine this feature with other features. Um, for example, if we take sepal length and sepal width, what if we maybe put a threshold right here, right? That would
Right.
work.
Yeah, it would definitely work. I mean, you might miss just one or something, but it would be very effective.
Yeah, in
You
that
might be able to
case,
get all of them.
we're thinking about uh, the logistic regression, but thinking about, you know, um, the KNN, how the KNN would work here. So suppose you have a new point right here. depending on your k, like if it's
Hmm.
3, 5, 7, or even 1, you would count like how many points are closer to this point, and then you would get the voting of the majority class, and then say this is orange, like versicolor, or green Virginica, etc.
Mm.
Okay, so this is a good way to look at the features, um, analyze what's going on, which ones we can use, which ones we can maybe remove because they're highly correlated. So we might be able to remove one. Okay, so instead of looking at everything here, I'm going to do a classification between versicolor and Virginica only.
Mm.
Um, so I'm going to create a new data set. Just, yeah, I'm going to call temporarily X no setosa and Y no setosa. And I'm going to recreate X and Y. And then I'm going to do something. Um, so in order to train our models and to test our models, we need to use different data sets. I think we talked a little bit about that last time. Uh,
Yes, yes. We talked about the training set and then also the testing set.
exactly. And luckily, scikit-learn has, one
Mm.
function exactly for that called train test split. So we need to pass our X, our Y, the test size as a percentage. So here I'm saying, let's split in 30%. So I'm going to use 70% to train and 30% to test. This is just a parameter to make sure, these learning algorithms are random, and we want to make things reproducible every time we rerun it. So there's something called random state
Hmm.
or seed. So basically defining, you know, a, a given number always. Every time you rerun this, this will generate the same results. Okay, there's also another parameter here, stratify. So stratify will make sure we'll split evenly between training and test. So instead of having like way more Virginica in the test set, we're trying to make
Mm.
the classes balanced.
I
Okay.
see.
All right. So when we run this cell, we have training set size, um, 70, and the test set size 30. Okay, so we have two variables here, x train, x test. And now we're going to run the actual models to make the predictions, right? Um, okay, so I'm going to create a variable called logreg that will
Hmm.
be an instance of class logistic regression. So first we just create this class, and then we're gonna run this function called fit, and we pass x train and y train. So what's the fit method or the fit function? So basically, we are, you know, passing these 70 samples to the algorithm, uh, so that the model starts learning um, about the patterns, right? So this is the point um, where the model will try to decrease the error, decrease the number of mistakes that it's making, as we saw last time, um, but not um, trying to, learn too much about the training sample. So we have to create a model that is good for the training sample, but also will be good for the test sample,
Mm.
meaning that um, it's a general model instead of, um, you know, creating overfitting. We can also discuss about overfitting in future sessions, but for now, let's just keep in mind we're getting the training um, set, the x and y, and we're passing to the model here in this dot fit. And then we're going to make predictions. So the predictions will be um, from this method called predict. And now, yeah, after we run this line, we have a model that's trained, right? And there are some weights that we can check. Maybe I can explore a little bit. Um, and then if we do predict and pass a new set of values, this will make predictions. Let's run this real quick. Um, and then I'm plotting just the accuracy here. Um, well, those numbers are not very important for now. Let's just, um, yeah, keep in mind these are very good numbers. So I'm trying to predict versicolor, virginica, and this is calculating precision, recall, F1 score, and giving the support. The accuracy in this case will be 0.93. This is because it's actually not so hard to, using different features to separate these classes. There will be some mistakes sometimes, but even by using two variables, we can almost separate, perfectly here.
Mhm.
So actually adding more variables, we can do even better. Um, okay, so um, okay, so we're here. So these numbers are really good. We talked about what's precision in recall and F1 score last time as well. These are based on the true positive, true negative, false positive, and false negative. Um, you can always go back to interactive ML to recall, um, to remind yourself about what the metrics are. Okay, so this is what we have for the logistic regression. As I said, you can explore um, some parameter. Well, this is the model that was trained. Um, there are some things you can explore here. For example, the coefficients, the intercept. This is something we saw last time. So if you do log reg coef, this is really nice. This is how
Mm.
we're multiplying the values to generate the classification, right? So this will be multiplied by the flower sepal length. The second number will be multiplied by the sepal width, and so and so. There's also the intercept, which is negative or minus 15 point blah blah blah. This is pretty nice. So this is just showing how the function, the logistic regression, um, will be created, right? So as you remember, we had something like um, y equals m times x plus b. So b is this number in this case,
Mhm.
and the x's will have like x0, x1, x2, and x3. Um, this will be, well, actually, these are the weights, right? So this will be the m0, m1. The x that will come is the actual value of a new sample, right? So
Right.
anyway,
That's really good for the audience to know, right? The M is in this case the weights.
yeah, m will be the set of weights. Um, okay, so what happens when we do um, the same thing with the KNN model, right? So it's nice. What's nice to see is basically um, the code is basically the same, right? The only thing that changes is how you call the model here.
Hmm.
But yeah, the dot fit will be the same. Dot predict also to calculate the accuracy. So let's run this. Boom.
Wow, amazing. Very much
Yeah,
the same flow.
pretty much the same thing. Here I'm doing something to remove the setosa from the target names. But basically, yeah, basically the results um, are calculated the same way. There will be some things differently. Let me see. No, accuracy, macro average, weighted average. Um, yeah. So there are, some things you can consider if the classes are not balanced. For example, if you have more um, of one class than the other, then you can change some things in the model to make fair predictions. But yeah, we're not going to talk about that today. This is just a way to compare the results. Oops. Yeah, so the accuracy of the logistic regression
Mhm.
was a little higher. Um, Let me see. So precision point, yeah, 0.93, 0.87. Let me see. Yeah, I guess it's comparable, but in general, the accuracy is better for the logistic regression. Let me see the F1 score, um, 0.94, 0.93. Yeah, compared to 0.90. So F1 score of the logistic regression is better as well. Um, yeah, so the last part here is just, um, some fake data. If we want to make predictions on new data points. So here, as we, yeah, interestingly, um, this is a point that was created to be a likely setosa,
Mhm.
but we removed setosa from the models. So this was predicted as versicolor, right?
Right. Yeah, that makes sense.
Yeah. So if you let me see, if you look here, uh, versicolor is actually more similar to setosa than
Right.
virginica, right?
Yeah, yeah, especially
So
on the cluster and also for the logistical regression. So,
yeah. So yeah. So this is the end of our first analysis. So we went over basically, um, the whole process, which is, loading the data, training the models, testing the models, and looking at the results, and also doing some EDA or exploratory data analysis at the beginning. But I have to say, this was a very simplified version of what people do. Usually, we have to iterate over these steps a few times. Uh, the data is not always as good as this. Can't see separation most of the times. Um, and in some cases, it's impossible to look at all the variables because there are too many. So you have to, you know, do some, pre-analysis first, looking at, missing data, what you're gonna do when you have unbalanced classes, um, or if you have correlated variables, you can remove them. But this is the process, and also our predictions are pretty good, right? Um, we don't have so many variables, so we used very very simple models. Um, in real life, people use not only these models, but you can include like random forest or XGBoost or even neural networks. We'll talk more about that in future sessions. But for today, I just wanted to go over uh, the code to load the data, do the analysis, make predictions, and compare results.
Well, wow. Such an impactful and educational session today. Really appreciate you sharing, the code and the flow and showing everyone how possible this is for everyone here. And we're really excited to, make this accessible for everyone. We'll be dropping um, the Jupyter notebook and the code in the description here and on a GitHub repo for you to access at any time. So, Leandro, that was amazing. Thank you for sharing so much information about logistic regression and the K nearest neighbor. Phenomenal, and absolutely, as you mentioned, so much data cleaning that's involved as well to make
Yeah.
this stuff run, right? I'm sure you're dealing with that at, Block and formerly at Meta. So much more data, right, than this.
Yeah, in huge um, institutions, like when data is not a problem,
Mhm.
sometimes people do not care much about um, cleaning the data. Oh, let me rephrase that. People don't have to look at the data like as close as if we have fewer samples, right?
Right.
Usually, you just apply data transformations. You have to look at the distributions, um, and it's a nice topic to go over, and we'll go over in future sessions about feature engineering, right? So this is what people do. Like, so if you have age as a raw number, is it better for the model, or is it better if you just create um, you know chunks, like different buckets of ages, like if it's a teen, if it's a young adult, if like adult or older people. This would make more sense for the model than just a raw number. um, or maybe, instead of using a zip code as a number, which doesn't make much sense, right? We'd have to transform the zip code, somehow. So all these things are called feature engineering. and that's done, um, and the model just runs, just learns from it.
Wow, that's very insightful. I can't wait for that next session on feature engineering. That one's
Yeah,
going to be very, very useful. And so, a lot of people are intimidated, as we kind of talked about in the beginning, about machine learning, right? And machine learning models. But it turns out, as you're mentioning, I mean, there's a lot of different type of models, neural networks, et cetera. But in a lot of, at the end of the day, it's all statistics, right? So these are just
yeah,
statistical models being run in a particular flow. Is that right?
yeah. It's just the computer learning about patterns, and everything is based on those functions like dot fit, dot predict, um, and calculating the metrics, and that's it. That's how you do.
Amazing. Nice. So when people are trying at home some of these models, they're making toy models, playing with their own data, which ones would you recommend for them to start out with first? I'm guessing potentially the logistic regression and the k nearest neighbor.
Yeah, so it's good to learn the basics instead of just using deep learning. Um, I think in some cases you don't need much to make good predictions. So in real life, people have to deal with trade-offs, right? So sometimes, um, if you have something simple, it will run much faster. It won't be slow to learn and to make predictions. So, you know, in a lot of cases, a simple, not that it's that simple, but an XGBoost would solve the problem instead of like a huge neural network,
Yeah.
So,
So great, right? And I can't wait because we're gonna be talking about all these different type of models that everyone can start be exposed to. Because by being exposed to and learning about them, then people will learn which ones to use in which context, right?
yeah, yeah. Just, yeah, keep practicing. Always when you're learning, try to compare different models, making predictions to your data. Um, Sometimes the 0.01 gain in accuracy, it's not worth it. You know, just use the simpler model, and it will be easier to explain. Yeah,
Yeah, and sometimes when we talk about prompt engineering, right, we say it's an art and a science, right?
yeah, yeah.
It's a lot of it's art as well, right? Trying to figure out from an intuitive basis what works and also what works for you, as well as following best practices, role instructions, etc. How much of machine learning is an art versus a science?
Yeah, so I think the art part would come from knowing exactly, like, how to compare different models, how to do the feature engineering, um, and maybe looking at how the metrics compare to each other, because these are just numbers, but sometimes you have to make decisions um, based on what you see. So this is the art part of it, um, which is, maybe you've seen something in your career and the best decision was to do this. Like, go with the simpler one. It depends on, as I said, like if you want the model to be explainable, or if you want it to be faster. If you don't care about it, like if you just want to make good predictions and you don't care if it takes a little longer, then go with a more complex one, you know.
Yeah,
But yeah, you always have to make sure you compare the results.
amazing. I love that, right? That's super exciting. And what we're trying to show here, right, is that machine learning is is not only extremely useful, but it's also very fun, right?
Yeah,
There's
yeah,
ways that
it
we can
is. It
play with,
is.
right? Yeah. I remember your last, when we were closing the last episode, how you were talking about, why you like machine learning. So I do recommend if people miss that, to watch the previous one and to figure out, to find out more about why, machine learning is fun, and also just as part of the art of it too, right? It's fun,
Yeah,
it's useful. And Leandro, thank you so much for doing this. You're making machine learning accessible for so many people around the world. Are there any
of
closing
course.
thoughts that you have about, that you'd like to close with?
Yeah, just don't be afraid of trying different models, playing. Now, we have AI to help us create notebooks and to change what we have, right? Don't be afraid. Ask, I don't know, Claude, ChatGPT, hey, let's create an analysis to uh, analyze, this data set. I don't know. Talk to the AI. The AI will be helpful to teach you as well.
That's amazing, right? Using AI to learn more about machine learning and AI.
Yeah,
So it's how meta. So amazing. Thank you so much, Leandro, for this, and I
of
can't wait
course.
for the next one.
Yeah, me too. Me too.
All right. Have a good one, Leandro, and take care, everyone. Bye.
Bye.